Well, hello and welcome back to Engineering 211 Statics, and I wanted to pick up where we left off last time talking about shear and moment diagrams and specifically practicing those. We talked about the shortcut method last time, and I wanted to get some practice doing that. So I'd like to start with this problem here. We have a cantilevered beam and a continuous constant distributed load on it. Cantilever beam is 10 feet long and the distributed load is 100 pounds per foot. So the first thing that I'm going to do, and we'll see that I maybe in the future could skip this step, but I'm going to do like we said, excuse me, and find the reactions. So I'm going to have some support reaction there, some force F, and some support moment M, and then we've got this distributed load that's 10 feet, 100 pounds per foot, and I could say that that is equivalent to the area under there is, better get a little better pen for this. It's a little messy. Let me tidy that up. So 100 pounds per foot. So if I found the area, this would be then 1,000 pounds, wouldn't it? And that would be located at the centroid of that area, which would be at the middle, 5 feet from either end. So if I sum the forces in the vertical direction, setting those equal to 0, I have F minus 1,000. So I can say that the reaction F is equal to 1,000 pounds. And then if I sum the moment at the left-hand side, setting that equal to 0, I have M minus 1,000 times that distance of 5. The force F intersects that point, so I could say that M is equal to 5,000 pound-feet. Now, I'm going to use that to help me draw the shear and moment diagram. I'm going to use the shortcut method here. I'm going to start at the left-hand side. So there's our shear. It's in pounds. And we'll start at 0. And we know that the shear changes by the minus the area under the load. So the area under there is 1,000, isn't it? Okay, and I put a negative sign. So I'm going to go from 0 to minus 1,000. And how do I get there? Well, I know that the slope of the shear is equal to minus the value of the load. So I take this constant positive, and I put a negative sign on top in that constant positive, so I have a constant negative slope. So I have something that looks like that. Now I'm seeing down here at this minus 1,000, and I come back and I look at this reaction, so I get to jump up, because that reaction would be applied, so I jump back up that 1,000. So indeed I do get back to 0. So that's the shear diagram. Now the moment diagram, let's see what that looks like. That's going to be in pound-feet. And what happens here? I know that the moment changes by the area under the shear. So the area in here is equal to 1,000 times 10 divided by 2, because it's a triangle, and it's going to be negative because it's below the line. So I would have minus 5,000. And again, you don't normally put these values on it here. I'm just trying to show you where those came from. So I have minus 5,000. So I'm going to go from 0 to this value down here, minus 5,000. And how do I get there? Well, the slope of the moment is equal to the value of the shear. So I start out with a small negative value, so I'm going to have a small negative slope, and I'm going to go to a larger negative value and give me a larger negative slope. So I get something like this. And then when I'm down there at minus 5,000, remember this moment, this is clockwise. A clockwise moment produces an upward jump. So I can jump up. I jump up that 5,000 takes me again back to 0. So a few things that I want to look at before we leave this problem. You'll notice that the order actually increases, and this is a very common. We have constant, in this case, we have a constant value. Here we have a triangular or linear value. So we go from a constant to a first order, and here we have a second order. Okay, a second order curve. So you're going to see the orders increase. If this would have been a triangular load, then we would have got a second order curve here and had more trouble finding the area under it. Although if we knew the reaction, we probably could have put that in. Which brings me to the last point in this problem. Technically, I really didn't need to do this, because if I started here at the left-hand side and worked to the right-hand side, I would know what that was. Although I think it was kind of nice to know when we got down here to 1,000 and saw that this was 1,000, that we really did get the right answer. But if you were really in a hurry, you wouldn't necessarily need to get the reactions on this one, but it's probably always good to do each piece properly. Well, there's your shear and your moment diagram for that problem. Let me move on then to the last problem that we're going to do in this area. And this is a fairly involved problem. When we study this again in strengths and materials, spring term, we'll probably see this problem again. I think if you go to the website, I've got it posted up in the notes section to help you with this, but you've got the PDFs from this lecture here too, and I'll put the website in the comments of this video like I always do. But I think if you can sit down with a problem like this and go through this, I think you've got this concept very well at hand. So what we have here is we have a continuous beam, and we have a cantilevered section here, and then we have a simply supported section between A and B. We have a constant distributed load, we've got a triangular load, we have this concentrated moment there. So a lot of things going on. So I'm going to come up with a shear and moment diagram. Before I do that, I've got to get these reactions. So I'm going to skip ahead a page then. And I'm going to get these reactions. Remember, with the shortcut method, there is no substitute for getting the reactions. You've got to get the reactions, and you've got to get them right. So it's important to practice that. Well, in finding the reactions, what I might do is I might sum the moment about B. So summing the moment about B, setting that equal to 0. Maybe I'll go ahead and take counterclockwise as positive. What I can do is I can say that I have, let's see, what's this going to be? This area in here is going to be 6 times 100. Isn't that going to be 6 times 100? So it's 6, and we have 100 there, and then I divide it by 2, so that's 300. So I can say that I have 300 times, and this is going to act at, this force would come down through here at 1/3 of this distance. What's 1/3 of 6? 6 over 3 is equal to 2, isn't it? Okay, so I'm 2 plus 6 is 8, plus another 2 is 10, plus 2 more is 12. So I have 300 times 12, and again that's 2 to there, 6 more is 8, 2 more is 10, and then I have this distance 2 because it's 1/3 of that distance for 12. Now I'll have to add to that. What am I going to have? 200, isn't that this one here? So this would be 200. And what distance is that going to act through? Well, it's going to be a foot from there, isn't it? It'll be 1 foot. So I have 2 and 6 is 8 and 1 is 9. And you could do this distributed load all as one if you wanted to. I'm going to break it into two pieces. So I'm going to have then, 600. And that's going to act through this distance here, which is going to be 3. So I've got 2 and 3, that's 5, right? Okay, so if you wanted to take this at 800 acting at the center there, you could, but I took this piece here, this little piece right here, as 200 acting at 9, so 8 plus 1, and this piece 600 acting at 2 plus half of 6, half of 6 being 3, so 2 plus 3 is 5. So that's got that taken care of. Then I had probably better subtract off this 2,000, because that's got to be factored in. This free vector, you got to add that in no matter where you're doing this. And then I'm also going to have to subtract off a times the distance that acts through, which is 6 plus 2, which is 8. So I can say in solving for a that a is equal to 300 times 12 plus 200 times 9 plus 600 times 5. And then I'd have minus 2,000 divided by 8. So A is equal to, I think my number on that was 800 pounds. Let me double check that for you. Yep, 800. So good. And we could do another moment equation. I could sum the moment about A to get the B values, or I could sum the moment about here and then have to do a simultaneous equation with to get A and B. But I think probably this made good sense. Summing the moment about point B, because I have two unknown forces there. Bx should be pretty easy though. If I sum the forces in the horizontal direction, setting that equal to 0. Bx is the only thing that is in the horizontal direction, so Bx is equal to 0. How about summing the forces in the vertical direction, setting that equal to 0? We'll go ahead and take positive up on this. I would then have A plus By minus, what did I have? Minus, this was 300, wasn't it? Minus 200 minus 600. Is that it? 300, 200, 600. I've accounted for that one and that one. Yeah, I think we're good. Now I'm going to put A in here. We'll put that 800 in there. And we've got then that By is going to be equal to 300 plus 200 plus 600 minus 800. So By turns out to be equal to what? 300? Okay, and you'll notice you don't have that concentrated moment in here. Does it affect B? Oh, absolutely, because you see that I'm sorry, I think I said 2,000. So we don't see that 2,000 directly in here, but we see that 2,000 in there, which is affecting A, and then A is substituted in. So it doesn't show up directly in the force equation, but it is affecting the force equation. So I've got those values. Bx is 0, By is 300, and A is 800. And you got to get those. You got to get them right. So moving back to this, I can put these on here then. This A was 800, and this B is 300. And we would expect with a cantilever section to have this A very large. And in fact, if we took this moment off, this would be much, much larger. So this is a very common arrangement to have a reaction like that. So where would we get something like this? And if we run over here to page 4 real quick. Sometimes in houses, maybe you'll see a 2-story house. And you can get this in all kinds of places, but I put this maybe in a context that we might look at a roof like this. So sometimes you'll see a house like that. They cantilever the front over to give them a little more room upstairs, make the front not just one great big wall. And if we were to then model a beam like this, we would have a reaction over here where this bottom wall is supporting it. We then have a reaction here like this. Of course, this roof is loading here and coming down, isn't it? So we'd have this great big concentrated load there. Then we have all the people up in here and the, hot tub and all that stuff that would account for the distributed load like this. So not exactly our problem, but a similar problem in terms of cantilever section and whatnot. You usually look at this reaction here, R1 and R2, that R2 is a lot larger than R1. Well, anyway, so we'll find these things in real life, certainly. Let's run back here. And now that we've got the reactions, horizontal is 0, so I won't clutter up the picture with this. We should be ready to go. One thing I might do is the areas here. Wasn't this 300? This was 200, and this was 600. And this actually brings up a really good point that I haven't talked about too much till now. But you cannot use this concentrated force here to do the shear and moment diagram. We use that concentrated force 600 to get our reactions, but you can't use it to do your shear and moment diagram. And the reason for that is, let's maybe go back to this page 4. Well, we got page 4 filled up. Let's go to page 5. So let's say that we did a little problem. Someone took a table, and we have the center line of the table here. We've got the legs at this point. And we had the person laying on the table. Okay, like this. Always have to have a hat. And their center of mass here was at the center of the table. And conversely, we looked at a similar table, exactly the same table. And we had the center line of the table here, and we had this person then standing at the center line of the table like that. Would the reactions here and here be the same as the reactions there and there? And they would. Okay, if you've got the center of mass at the center and their center of mass there, the reactions would be the same. Under which case would the table be under a lot greater stress? Well, here the table would be under a lot greater stress, wouldn't it? Here it's distributed out. So we can see that the concentrated equivalent gives us the same reactions, but it does not give us the same internal loading, the same internal shear, and the same internal bending. Anyone that maybe has grown up in an area that has a lot of ice and whatnot knows this. When you facilitate an ice rescue, you don't want to walk out and try and help the person. You want to end up laying down and trying to help them, so you put the least amount of stress into the ice as possible. And I guess you could go into ice design. There's people that actually do that when they build the highways on ice during the winter and things like that. And talk about making ships out of ice and all of those kind of interesting things. Anyway, I will run back and get back on task here. So while we use these concentrated loads to get the reactions, we do not want to use the concentrated loads to build the shear and moment diagram. Well, I'm going to start my shear at 0, and what happens, it changes by negative the area under this. So all of a sudden I'm going to drop down to minus 300, right? I'm subtracting 300, and how do I get there? Well, I start out with a small positive value, so I put a negative sign in front of that, and I get a small negative slope. And I go to a larger positive value, so I'm going to have a larger negative slope. So I'm going to have something like that. That's going to be second order. Now the area under here, that's 200, so I keep on decreasing because minus 300, and then I subtract off 200 because it's the area under the load. So minus 300 minus 200 gives me minus 500, doesn't it? So I will be then right there. And how do I get there? Well, constant positive value. So put a negative sign in front of that, and I get a constant negative slope. So this is linear. This is first order. This is parabolic, second order. Then what happens? I jump up. So I'm at minus 500, and I jump up. You're at minus 500 and you jump up 800, that's going to take you to positive 300, isn't it? So I jump up, And sometimes people will even put the arrow on it like that. So you're sitting at 300 now. Then what happens? You start dropping down again. How much do you drop down? Well, 600. So you take the 600, you put a negative sign in front of it. So we're going to end up right back down here, aren't we? Like that, at minus 300. Easy come, easy go. We go from positive 300 back down to minus 300. Does this show up? Not directly. Did it affect the reactions? Yeah. So it will show up indirectly, but not directly on the shear diagram. Then what do? Well, I just continue on. A lot of times people, they like to jump back to the 0. That's not true. We just continue on. We continue on. We're at minus 300. What do we encounter? This 300 up. So I get to jump up from minus 300 up. I start and end at 0. Okay? So this is our shear diagram. Now there's a couple of things I'd like to know. Where this crosses is probably going to be fairly interesting on the moment diagram. And how do I know where it crosses? Well, this one's pretty easy, but let me go through that quickly for you. If I take this as x, and then this is going to be 6 minus x, I can say that x is to this side, which is 300, as 6 minus x is to this side here, which is 300. I mean, it's minus 300, but if we look at similar triangles, we can just say that it's 300. So I could say then with that x is equal to 3. And a lot of times it's not that easy, but that's how you do it, by similar triangles, because these are indeed similar triangles. They share that angle there and that angle there. They're by definition similar. So we know that distance is equal to 3. Okay, so let's start the moment diagram. One thing as we start the moment diagram, we're going to start at the left-hand side. We're going to start at 0. We always want to remember this thing. We don't have that many concentrated moments, so sometimes it's easy to forget those, and I guarantee if we forget 2,000, we're not going to end at 0. So let's do this. We start here, and I immediately encounter a problem. I'm trying to find the area under there, right? Okay, the area under here, this second order, area under a second order is hard. So what I think I'll do is I'm just going to take a real quick section right there. And when I take that quick section, so I'm going back to the old school, giving up on the shortcut momentarily. I use my deformation sign convention. There's the shear. There's the moment, right? Okay. And because we took that section right here, we took it at 6. So I know that this is 100 up here. 100. So I can say that if I sum the moment about the cut, what am I going to have? I'm going to have this area here, which is 6 times 100 divided by 2. That'd be just right there, wouldn't it? And then it's going to be acting at a distance of 6 over 3. And then I have to add the moment m into it. Okay, so I've accounted for this force acting at this distance. That's that thing. And then I've got the moment m, or this distance in here. That's 6 over 3. So I can say that m is equal to, what's this thing, 600 over 2, 300 times 2, right? So it's minus 600 pound-feet. So when you get good at this, you can almost do that in your head. You notice I didn't sum the forces. Had I summed the forces, what would I have? Some of the forces in the vertical direction, setting that equal to 0. I have minus v minus 300. Isn't that the area under there? So v is equal to minus 300, isn't it? Have we seen that? Absolutely. V is equal to minus 300. So I didn't necessarily need to do that. Okay, so I now know that I'm going to get to this point here. This is minus 600. Minus 600. And how do I get there? Well, it's going to start out with a very small negative slope and go to a very large negative slope. So I'm going to have something like that. It's going to be third order. This is linear. This is, this is linear. This is second order. This is third order. Now I need the area of this trapezoid, don't I? Let's see, what's the area of that trapezoid going to be? I take the two sides. I've got 300 plus 500 divided by 2, so I average the two sides, and I'm going to be multiplying this by 2, so that should be, what, 800? Okay, it's below the line, so we're going to have a negative 800. So if I'm at minus 600 and I subtract 800, that takes me to minus 1400. How do I get there? Well, this is linear, so I'm going to get there by second order. Okay, so this is third, this is second. Okay, which hopefully makes sense. I have a constant, I go to linear, I go to second order. Then what's going to happen? Well, I don't have to jump by the force, but I do have to start dealing with this positive area here. What's the area in that thing? Well, we could say that A is equal to 300 times this 3. That's why we had to find what x was, times 3 divided by 2. That's what, 450? Okay, it's positive 450. So if I am at minus 1400 and I add a positive 450 to it, where's that going to take me to? Minus 950. That comes from minus 1400 plus 450. How do I get there? I start out with a large positive slope. I go to a small positive slope. So I'm going to do something like that. First order, second order. Well, what's this area here? Well, that's minus A, isn't it? And again, you usually don't put the clutter up the diagram here. I just want you to know kind of where these come from. So I'm up here at minus 950. I subtract now 450. Takes me right back to where I started, right? Minus 1400. And I get there the same way. Easy come, easy go. So I'm sitting at minus 1400 now. And our temptation is to just find the area under here, but what do I have to do? I have to come up and look at this concentrated moment. I have concentrated 2,000 pound-feet. So I'm at minus 1,400. I'm going to jump up 2,000. So where's that going to take me to? That's going to take me to 600, isn't it? Okay. So I'll have 600 there. Now what's the area under here? Well, it's minus 300 times 2, minus 600. So if I'm at positive 600 and I subtract 600, that takes me to 0. That's good. How am I going to get there? Constant negative slope. Constant negative value, constant negative slope, like that. So I started at the left at 0, I ended at the right at 0, and my diagram looks like this. Okay. Well, hopefully this is useful. Now, if I have the electrician or the plumber wanting to drill holes, and they say, well, we can drill a hole here, or we can drill a hole here, looks like we'd probably be a lot better off drilling it out there than right there. We've got a lot of internal stresses around, well, we have a lot of internal forces, I should say, around a spring term we'll talk about and convert those into internal stresses. So I think we are good with this. Again, we go from a constant, then a first order, and then a second order. Some people might say, well, you still had to do the section here. Well, what if we hadn't have done this shortcut? How many sections would we have done? We would have done a section here, we would have done a section here, we would have done a section here, and we would have done a section in here. And I guarantee even this section would have been more difficult, because instead of 6, this would have been x, which is quite a bit more difficult than 6. So And this wouldn't have been 100. This would have been some function because you're taking the section in there. So I think the shortcut method is definitely good. It's worth learning. We're going to talk about it and use it a lot. So I would really dig in and concentrate on that. Like I said, if you can sit down and you can tackle a problem like this, which I would do again and again, I mean, take this thing and start out with it like that and make sure that you can get those reactions. That's good review for the final. And then make sure that you can draw the shear in the moment diagram. I think if you can do something like that on a problem like this, you are really in pretty good shape. Well, where does that put us? We've finished up with internal forces, with shear and moment diagrams, and we're ready to move on to friction. So when we get together next time, we'll talk about friction, dry friction that is, and continue on from there. So thank you for watching, and take care till next time.